Okay, this is Math 116, section 6.4, and this one's going to be present value of annuities. So we still have the same two kind of annuities. We have the ordinary annuities with the payments at the end, and the annuities due with the payments at the beginning. But this time we're looking at present value instead of future value. And as I go through the examples out, we'll hopefully get a little bit clearer as to the difference. But basically, present value is the money in hand today versus the money we would have later. Everything else in terms of our two little formulas and all of our definitions are all the same as the last section. So I'll just head into a problem here. Okay, question 1. Find the present value of an annuity of $9,000 paid at the end of each 6-month period for 2 years if the interest rate is 8% compounded semi-annually. So find the present value. I forgot to point out present value is A. And so that is what we're trying to figure out. And the, let's see, present value annuity, $9,000 paid at the end of each 6-month period. So that's our payment. Is going to be $9,000, and then just like in the last section, at the end, so that means this is ordinary annuity, and then a little later in the section we'll see annuity due with a similar but slightly different formula again. Let's see, the time is 2 years, interest rate is 8%, and compounded semi-annually, so M is 2. So then for N, times compounding periods, N is going to be 4, and I, remember, is rate over compounding periods, so that is going to be 0.04. And then we're just plugging into the formula, so just like last time, I'll write it out this first example, and then I'll just plug straight in after that. Okay, so here's the formula for present value of an ordinary annuity. And then I'm just going to plug all this in. So we'll have A, payment again. Very similar to the last section, just things are rearranged a bit. I was 0.04, negative N, and then I, again, 0.04. And so this one is just shoved the whole thing in a calculator, and when I did that, I got 32,669.06. Okay, and then again, since this is the first example, let me go back and kind of say what this means relative to this present value thing. So what we found was the present value, the amount of money that it would be right now for an annuity to pay $9,000 at the end of each 6-month period for 2 years. So that would be 4 payments of $9,000, so that would be $36,000. And if we had $32,669.06 right now, we could put that in an account under these terms, and it would pay out $36,000. So you can see a little bit more than what you're investing over the 2-year period. Okay, number 2, if $83,000 is invested in an annuity that earns 5.7% compounded quarterly, what payments will it provide at the end of each quarter for the next 2.5 years? So this time we are looking for what payments. So we're looking for R. So $83,000 is invested. So that means right now today we have $83,000 and we're putting it into that annuity. So that is going to be our present value. Earns that rate, so 0.057. Compounded quarterly, so M is going to be 4. What payments, that's what we're looking for, are at the end of each quarter for the next 2.5 years. And so time is 2.5. They're two calculated values. N, so that's M times T, so that would be 10. And then I is R divided by T, and that comes out to 0.01425. And so then I'm just going to plug into that same formula as last time. This time we won't know R and we do know A, so we'll have 83,000. That's how much we have today. So what payments will that provide is what we're going to find. And then there'll be 1 minus 1 plus this number, so to the negative N, so negative 10, and then all over I. so 0.01425. And then tossed all that in the calculator. This should come out to 9.258, and then divided it over. And that gave me $8,964.31. So this would be our payments with that. If we put this in annuity, that would be our payments for the 2.5 years. Okay, and then this next round is going to be present value of annuity due. So these are the ones with the payments at the beginning of the period. So just like in 6.3, very similar formula to what we were just looking. It just has, once again, this extra little piece on the end that accounts for that extra payment. And I think we are familiar with all of the definitions, so I'll just head straight into the problems. So number 3 goes, find the present value of an annuity due that pays $2,000 at the beginning of each quarter for the next 7 years. Assume that the money is worth 6.6% compounded quarterly, round or cent. Okay, so we're finding the present value, so that was A. So that's our what we don't know. Pays $2,000 at the beginning of each quarter, so beginning, that tells us it's due. And just like in the last section, there'll be some problems where it has the pick, is it due or ordinary? And so those are coming up in a second. But so this one's going to be beginning of the period, so it's annuity due. 2,000 is our payment. And let's see, we got each quarter 7 years, that's T. There's our rate, 0.066, compounded quarterly, so M is 4. So I think we got all those, and then we still need I. So I would be the 0.066 divided by 4, and I think that doesn't come out nice, so I left it like that. And, oh no, it comes out fine. Sorry, I just saw it down below in the notes. 0.165. And then we still need N, which is going to be M times T. So that will be 28. So we got our list going, and now we're just going to take all of that, and I'm subbing into this formula right here. And so that will look like A equals 2,000, 1 minus, and then this is the 1 plus this, so 1.0165 to the negative 28 all over I, so this part again. And then that's times this piece. And then throw all that in the calculator, and I got, it was worth $45,292.52. Okay, number 4, a year-end bonus of $20,000 will generate how much money at the beginning of each month for the next year if it can be invested at 6.06 compounded monthly. So for this one, we're going to know the present value. We got this $20,000. And we're going to invest it so that we get payments at the beginning of each month for the following year. So the payments is what we're trying to figure out how much we're going to get. M, let's see, was 12. And then T is 1. And then our rate was 0.0606, and then N in this case, since the year is just 1 year, it's 1 times 12, so that would be 12, and I is this divided by 12, and that made 0.00505. And then once again, I'm just throwing all that in the formula, so I'll just copy it down over here. Okay, so here it is. I ran out of room for that last little bit there, but it's being times by that. So threw all this in the calculator and got 20,000 equals R. And then this came out to like 11.67, kept going, divided it over, and that gave me payments of 1713.23. Okay, number 5. An insurance settlement of $3 million must replace Trixie Eden's income for the next 45 years. I actually looked up Trixie Eden to see if there was some reason for that name, but I just thought it was such a hilarious name to put in a story problem. So anyhow, she's got $3 million, and that's going to replace her income for the next 45 years. What income will the settlement provide at the end of each month if it's invested in an annuity that earns 7.7% compounded monthly? So A, decide whether or not the problem relates to an ordinary annuity or an annuity due. So that's what I was saying was like in the last section. And then B, solve the problem. So this time, let's see, she is going to be paid at the end of each month. So that is going to make it an ordinary annuity. So we're using that first formula we saw. She has right now $3 million. And we're trying to figure out, the time was 45 years. And then how much will the settlement provide at the end of each month? So we're looking for the payment. If it's invested in annuity, 7.7%. And compounded monthly. And so for that, our N would be 45 times 12, and that comes out to 540. And then our little I would be 0.077 divided by 12. And that came out to something bad, so I just left it as 0.007 divided by 12. And then, again, I'll just cut away and toss all this stuff into the formula and cut back. Sorry, I just jumped in the notes. So this would be 3 million equals R, and then tossing all that into the calculator, which is not the easiest thing. I got 150, 916, ... Divide that over, and then my payments ended up, Trixie's going to live good. She's going to get $19,878.58, and I think that was monthly. Wow. Yeah, Trixie's going to do fine. Okay, question 6. Company wants to have $30,000 at the beginning of each 6-month period for the next 4.5 years. If an annuity is set up for this purpose, how much must be invested down in the annuity to earn if it earns 6.2% or 6.6% compounded semi-annually? So the idea is they're going to put some money away now, and that's going to produce a little bit more money and then make these payments that they're going to need to make every 6 months. And so we know the payments. We want to have $30,000 at the beginning of each of these 6 months, and we're looking for how much do we have to have right now today. So that is going to be, we're looking for present value. And this was at the beginning of each 6 months, so that's going to be an annuity due. So that's the formula with the extra little piece on the end. Payments are going to be $30,000. Time was 4.5 years. Rate was 0.0626 semi-annually, so M is 2. And then N, 2 times 4.5, so that would be 9. And then I, rate divided by M, so that'll be 0.0313. And so we'll do A equals, and then I'm just, again, going to set all this stuff up, cut away, and then cut back. Okay, so there it all is in the formula. Again, I'm just putting all that in the calculator. And I got, this came out 30,000, and then the kind of trickier piece was 7.98, and then 23,944.66. If I copy that down, yep. Okay, so the last thing in this section is, I think there's just 1 or 2 of these on the homework, and for me, I don't test on them, but they're in the section. So this is going to be the present value of a deferred annuity, and the deferred part will probably make a little more sense when I read a story problem that actually shows something being deferred, but it just means we're putting off payment on it, putting off getting the payments. Everything is the same except we have this K now, and that's going to be our number of periods deferred, and everything else I think is the exact same thing. So let me get to an example and explain what that does. So number 7 goes, the terms of a single parent's will indicate that a child receive an ordinary annuity of $17,000 per year from age 18 to age 24, so the child can attend college. And the balance of the estate goes to a niece. If the parent dies on the child's 13th birthday, how much money must be removed from the estate to purchase the annuity? Assume an interest rate of 5% compounded annually. Round your answer near set. Okay, so we are trying to figure out, there's like definitely a bunch of stuff going on, but how much money must be removed from the estate to purchase the annuity? So we're trying to figure out the amount that has to go in today to make that annuity happen. So that is the present value. The payments that are going to be made are going to be $17,000. Interest rate was 5%. Terms were, it was annual, yeah, so M is 1. And then we have to figure out kind of the K, which is the number of periods deferred, and then N, which is going to be the number of periods made. And that's where this gets a little bit tricky. So for the number of payments deferred, we'll work on K first here. So the parent dies on the child's 13th birthday, and they're not going to get money until the 18th birthday. So the birthdays where they get no money, 13th birthday, parent dies. So then on the 14th birthday, no money. 15th birthday, no money. 16th birthday, still no money. 17th birthday, no money. And then on the 18th birthday, that's where they start getting the 17 grand a year. So that was deferred 1, 2, 3, 4 years. So K is going to be 4. So that was this part. And then the back here, the N is the number of compounding periods times the time. So we have to figure out how long it's going to get paid out. So N will equal the number of payments made. And since this is annual, it's just times 1, so however many payments are made is going to be it. And so kid gets money on the 18th, 19th, 20th, 21st, 22nd, 23rd, and 24th. So you have to be a little careful, because they're going to get $17,000 on each of these birthdays. If you just go 24 minus 18, you get 6. But they're actually getting money on the end point. They're getting money on the 24th. So if we count them, 1, 2, 3, 4, 5, 6, 7 birthdays. And so N is 7. So now that we kind of have all of our bits and pieces, I'll set up the formula and then cut back. Okay, so here's everything plugged into the formula. And so it has this little tail end, and then that's where the K comes in, is it's the exponent for that piece. And then this one is our N, so this is the number of payments still, but this is the time deferred. And then I threw all that in the calculator, and I got 80,927.88 is how much they'd have to put away now to make those payments a few years down the road.